Okay, welcome back to part 3 of section 2.3, hopefully the last part of this. Our job in this section is to take more limits, but now we're going to be taking limits where we deal with issues. For example, I'm going to start here in this upper left-hand problem. We're taking the limit as x approaches 6 of x squared minus 36 over x minus 6. If I attempt to use direct substitution, I have 6 squared minus 36 divided by 6 minus 6, which means I've got 0 divided by 0. 0 divided by 0 is a bad, but it's a good bad thing. Okay, so I am ambivalent right now. 0 divided by 0 almost always means someone punched a hole in the graph. I'm sure there's a function out there where it doesn't, but almost always means there's a hole in the graph. A hole in the graph means the limit's going to exist, but I can't find it by direct substitution. So I'm going to use the factor and, what do they call it? Oh yeah, dividing out technique. So noticing quite easily that numerator is the difference of squares, I get x minus 6 over x plus 6 divided by x minus 6. And I'll look at this right here, and what's that? Well, that piece right there, that's the hole in the graph. That's the 0 over 0 that's causing us trouble. So we're going to ignore it, and we're going to turn our f of x into our new g of x according to the rule, take the limit of what's left by direct substitution, 12. And if the limit of the g is 12, then the limit of the f will also be 12. And so the limit of x squared minus 36 divided by x minus 6 as x approaches 6 is 12. And that's how we do these. That's how we deal with this problem. There are problems that we run into. We just need a technique to deal with them. All right, let's try another one. Right. Here we go. We're taking the limit as x approaches 2 of this hot mess. Right. Let's see. Plug into direct substitution. 2 cubed minus 8 divided by 2 cubed minus 2 times 2 squared plus 2 times 2 minus 4. In the numerator, we have 8 minus 8, that's 0. In the denominator, that's 8, that's 8, that's 0, that's 4, that's 4, that's 0, 0 plus 0, 0. We have 0 divided by 0. 0 divided by 0 is the good kind of bad. It's bad because we can't just use direct substitution, but it's good because then we should be able to use some sort of algebraic technique. Now, this one might be a little bit harder to see, but I'm hoping you see that numerator is the difference of cubes and is factorable. Do you remember the difference of cubes? A cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. Okay? So then what's that going to give me here? So the limit as x approaches 2 of x minus 2 times x squared plus 2x plus 4. I know what you're thinking. How am I going to factor that denominator? There's a hint in the problem. The only way that this thing is going to work is if we end up with this factor, x minus 2, right down there. So since we know what factor we need to factor out, we could just do long division and get it out of there. Right? Or whatever technique you use, synthetic division or whatever. So I am going to take and do, me personally, I'm going to do long division. So I'm going to set up my division problem. I've got x cubed minus 2x squared plus 2x minus 4. I'm dividing by x. Ooh, that was an ugly x. X minus 2. It's going to go in here x squared times, so that's going to give me x cubed minus 2x squared. That's a 0 plus 2x minus 4 plus 2. So then this factors into x minus 2 times x squared plus 2. What's this? That's the 0 over 0. That's the hole in the graph. That's the thing we're going to ignore. So then what's this? That's the g of x that behaves just like our original f of x everywhere except for directly at 2, but it's the piece we're going to use for direct substitution. And so we get 2 squared plus 2 times 2 plus 4 over 2 squared plus 2. 2 squared, that's 4. So we get highlighted. That's 4, that's 4, that's 4. So that numerator is 12. Our denominator is 6. And we end up with 2. And so we get that the limit as x approaches 2 of x cubed minus 8 divided by x cubed minus 2x squared plus 2x minus 4 is 2. That's not too bad. All right, let's try this one. Again, first thing we always do is direct substitution. 3 minus 13 times 3 plus 4 times 3 squared divided by 3 minus 3. Let's see, upstairs I've got what? 13 times 3. I got 3 minus 39 plus 3 squared 9, 4 times 3, 36. 0. Downstairs I have 0. 0 divided by 0. That means that this thing is, what is this thing? Oh, that's right. This thing is going to have a hole in the graph, and I should be able to factor it out. Right. Now, I already know what I need to factor out. I need the numerator to become x minus 3 times something, because the denominator is x minus 3, and that's what's going to give us our hole. So if I just factor out an x minus 3, I know I need a 4x, and I know I need a plus 1. Wait a second. No, I'm sorry. I need a minus 1 to give me that to be a positive 3. And so I've got the hole. I've got the g of x function. I've got the g of x function. I'll use direct substitution on it. That's going to be 12 minus 1 or 11. So then that means that the limit as x approaches 3 of 3 minus 13x plus 4x squared over x minus 3 is 11. Okay. So my job is to evaluate limits. The first thing I always try is direct substitution. Sometimes I get lucky and direct substitution just works. Sometimes I don't get lucky and direct substitution doesn't work, but it still gives me information about the graph. Right? 0 divided by 0 tells me something about the graph, tells me there's a hole in the graph. And if there's a hole in the graph, I can figure out where it is. Right? Even when direct substitution doesn't work and gives me asymptotes, like it did here, it still gives me something. So I always want to do direct substitution first. Right? All right, let's look at this one now. Again, we're doing direct substitution first because it'll tell me what to do. Square root of 7 plus 2 minus 3 divided by 7 minus 7. 7 plus 2 is 9. Root 9 is 3. 3 minus 3 is 0. 7 minus 7 downstairs is 0. 0 divided by 0. Hole in the graph, hole in the graph. Do some, This does not look like one that is factorable. So what we're going to have to do is we are going to have to use a different technique. Since there's a root in it, we're going to have to use the rationalizing technique. And the rationalizing technique says rationalize either the numerator or the denominator and then see what happens. That should say see what happens. Okay. This might require a little bit more factoring after we do the rationalization because sometimes these root ones can be ugly. Since the root is in the numerator, we will rationalize our numerator. So then this becomes the limit as x approaches 7 of the square root of x plus 2 minus 3 over x minus 7. We're going to rationalize by multiplying by the conjugate of the numerator. Okay. When I multiply by the conjugate of the numerator, I get the limit as x approaches 7 of, let's see, this is essentially a minus b times a plus b, difference of squares, a squared minus b squared. So we're going to get x plus 2 minus 9 over x minus 7 times the square root of x plus 2 plus 3. Now, if you're wondering why I did not multiply this out downstairs, it's because in the next step, I'm going to try to factor out the 0. So why multiply it out if one step later I have to factor it out? Okay. Take a look at the numerator. What's going to happen when we remove those useless parentheses? Okay. We're then going to get the limit as x approaches 7 of x minus 7 over x minus 7 times the square root of x plus 2 plus 3. Okay. There's the hole in the graph. There's a 1 as a placeholder because we can't just say there's nothing left in the numerator when we get rid of that. It's times 1. And then we've got our new function, g of x, that we're going to evaluate by direct substitution. 1 over 7 plus 2 is 9, so 6. Square root of 9 is 3. 3 plus 3 is 6. And so we get that our limit is 1/6. So essentially I'm doing similar techniques. I do direct substitution. I recognize 0 divided by 0 means a hole in the graph. I do the math required for a hole in the graph. If I see factorable stuff, I factor. If I see roots, I rationalize. Okay? Let's try this one. Direct substitution. What do we get? Three minus square root of 9 over 9 minus 9. 3 minus the square root of 9, 0. 9 minus 9, 0. I've got 0 divided by 0. And what does 0 divided by 0 mean? Do more work. Right? It's a hole in the graph. Figure out where the hole is. I'm seeing a root, so I'm going to try rationalizing. So that's going to give me the limit as x approaches 9 of 3 minus the square root of x over x minus 9 times the conjugate, 3 plus the square root of x over 3 plus the square root of x. That's going to give me then the limit as x approaches 9 of, let's see, there's a minus b, there's a plus b, a squared minus b squared, so 9 minus x over x minus 9 times 3 plus the root of x. I've got a problem here. These aren't the same. I got 9 minus x and x minus 9. Do those still cancel each other? I mean, direct substitution still gives me 0 over 0 right there. So this still is 0 over 0. But does 9 minus x cancel x minus 9? Sort of. It becomes this. We'll factor a negative 1 out to make it work. And now, there's our 0 over 0 that we can ignore. And we can do direct substitution on what's left. I forgot a parentheses right here. My numerator stays negative 1. My denominator becomes 6. And so we get negative 1/6. Okay. Now that's 2 problems in a row where we've rationalized and we've gotten 1/6, negative 1/6 and 1/6. Does that mean that all roots become 1/6? No, please don't think that. That's just a weird coincidence. All right, what's happening here? Direct substitution. That's what we always try. We're going to have 2 times 9 minus 9 minus 9 divided by 9 minus 9. That looks a lot like 0 over 0. So we're going to factor. Now this one's different. This is the first one where we had to factor both the numerator and the denominator. So let's look at a pattern here. If the whole's at 3, what is the factor that we have to be able to get? Right? Well, if the whole is at 3, we need an x minus 3 downstairs and an x minus 3 upstairs. We need the numerator to factor, so that one of the factors is x minus 3. We need the denominator to factor, so that one of the factors is x minus 3. Now, the denominator is the easier of the two because it's the difference of squares, so it's just x minus 3 times x plus 3. The numerator is going to be a little trickier. I know I'm going to need a 2x, so I can get that 2x squared term. And I think I'm going to need a positive 3. Let's check and see if that works. 2x squared, there's my first times first gives me 2x squared. Outer gives me 3x, inner gives me negative 6, negative 3, negative 9. We're good. All right, so right here, what's that? Well, that's the hole in the graph. That's the 0 divided by 0. So then this, that's the g of x that we talked about in that theorem up there. Direct substitution. We're going to get 2 times 3 is 6. 6 plus 3 is 9. And 3 plus 3 is 6 downstairs. 9, 6, or 3 halves. And so our limit is 3 halves. So all I'm doing is I'm just working through these problems and just doing the math that I have to do. Okay, this one looks tricky. I'm a little bit intimidated, but I can do direct substitution. 1/3 minus 1/3 over negative 3 cubed plus 27. That looks a lot like 0 over 0 to me. Hole in the graph, do something. Factor it? How do you factor 1/3 plus x? Does that factor? We're going to have to think about this one. Now, clearly, downstairs is the sum of cubes. So let's take a look at that. Maybe I'll just start down there and hope for some inspiration. The denominator is going to factor into x plus 3 times x squared minus 3x plus 9. Now I got to somehow get an x plus 3 upstairs, because if I don't, then I'm kind of stuck. So how can I factor? What can I do with that numerator? How can I make that give me an x plus 3? Because right now it's 1/3 plus x. Hey, what if I got a common denominator? Would that work? So what would be the common denominator? Well, this one would be x over x, and this one would be 3 over 3. So then that's going to be x plus 3 over 3x. There's my x plus 3 that I need. So now I can make it work. So now that becomes the limit as x approaches negative 3 of x plus 3 times 1 over 3x over x plus 3 times x squared minus 3x plus 9. There's the hole in my graph that I can ignore. This is the g of x from the theorem. And so now we're just going to do direct substitution on that g of x. And what are we going to get? Let's see, if I take a negative 3 and put it here, that's going to give me negative 1/9 for my numerator. If I put a negative 3 and put it into this mess, that's going to give me 9 plus 9 plus 9. That's 27 downstairs. Negative 1/9 divided by 27, that's going to be negative 1 over 80. Oh, no. 243? Yeah, 243. Negative 1 over 243. If you're wondering how that happened, you have negative 1/9 divided by 27. So that means negative 1/9 times 1/27. 9 times 27, 243. And so we have our limit is negative 1 over 243. So the limit as x approaches negative 3 of, was it 1/3? Yeah. Plus 1 over x over x cubed minus 27 is negative 1 over 243. This is a perfect example of one that I would never be able to figure out using numerical approach or a graphical approach, because that fraction is so small, I would assume it's 0. And I end up saying that this has a limit of 0, and I get it wrong every time. All right, I think this is the last one, right? Yeah, last one before we do Squeeze Theorem. Okay. Why is this one in this section? Because if I try to do direct substitution, I get 1 over 0 plus 1 over 0. So I don't know what that means. So I'm concerned. So how am I going to make this thing work? Well, let's see what we can do. Let's see, last time I had some fractions and they were giving me trouble, I got a common denominator, so maybe I'll try that here. All right? So I'm going to take the limit as x approaches 0 of, let's see. Just look at this denominator. Is that denominator right there? Is that x times x minus 1? So then my first fraction, to get a common denominator, is missing the x minus 1. Oh, wait, I don't want red. I want pink. And then my second fraction doesn't need anything. And now since these are, what do we want to call this? These are common denominators, we can combine them. And so what's x minus 1 plus 1? And so I'm to the blue. Now if I do direct substitution, 0 over 0 times negative 1, that's 0 over 0. And it's already factored. There's our hole. There's our problem. There's our hole in our graph. Remember, there'll be a placeholder of 1 upstairs. Plug in to the g of x. Use direct substitution, and we get then that the limit as x approaches 0 of 1 over x plus 1 over x squared minus x is going to be 1 over 0 minus 1, or negative 1. Okay. So, evaluating limits ranges from ridiculously easy, plug in the number, grind it out, to a little bit harder, where we have to do some algebra. The first couple were some pretty straightforward algebra, to some rationalization problems, which can be difficult. And then there's just some weird ones that show up. Okay? But when you see things in the problem and you don't know what else to do, try doing something obvious. I wasn't sure what to do. I'd never done this problem before. I see two fractions. Let's get a common denominator, see what happens. I see two fractions. Let's get a common denominator. Come on. Let's see what happens. And so it seems to work. So next time I see two fractions, guess what I'm going to do? I'm going to get a common denominator. The last thing is called the Squeeze Theorem. It's the last thing in section 2.3. And the Squeeze Theorem simply says that if you can find three functions, h of x, f of x, and g of x, such that h of x is the small one, g of x is the large one, and f of x is always somewhere between those two, and you can squeeze the bottom one, h, and the top one, g, together and give them the same limit somewhere. Okay? So you've found three functions, h of x, f of x, and g of x, so that you've got a small one, a medium one, and a big one. And the small one's always the smallest, the big one's always the biggest, and the medium one's always in the middle. Okay? And then you can find some place, some c value, where you can make the bottom one and the top one squeeze together. Where does the middle one have to be? Now, the Squeeze Theorem, also sometimes called the Sandwich Theorem, it's best shown in a graph. So you've got the small one down here, You got the big one up here, and there's the middle one. So you got baby bear on the bottom, you got Papa Bear up top, then you got Mama Bear in the middle. And then somehow we find a value C where we make the top one and the bottom one come together. And where is F? It's trapped in the middle. So F also has that same limit. Now, the squeeze theorem is an existence theorem. It just simply says, hey, if you can make this happen, you can find this. And so what it's good for is it's good for finding things that there's no other way to find. Let me give you an example right here. This is a limit that cannot be calculated directly. I cannot put in 0 and do direct substitution, and there's no algebra that I can do to work this thing out because of this stupid trig function right here. So there's no factoring out of a sign, or there's no rationalizing a sign, or there's no common denominators when there's a sign. I just got to find some other way to make it work. So what I'm going to do is I'm going to attempt to find 3 functions that make this work. Okay? And the way that I'm going to do that is I'm going to use a known property of the sine function. That is this. That for all x, an element of the real numbers, except for 0, because you can't do 1 divided by 0, the sine of 1 divided by x is going to be a number somewhere between -1 and +1. If you don't believe me, we can come back over here to Desmos because I love Desmos, and let's just take a look at the graph of y equals the sine of 1 divided by x. And you will see that if I were to also graph the line y equals 1, as well as the line y equals -1, that green graph is always between those two. That no matter how much I zoom in or how much I zoom out, that green graph is always bounded by those 2 functions. Let me make them nice and thick so you can see them easier. Okay? And then I'm going to make use of another known property, and that is that x squared is greater than or equal to 0 for all x elements of the real numbers, and x not equal to 0. Actually, I'm going to make it just be greater than 0. Because if it's not equal to 0, it's always greater than 0. Then I'm going to make use of a property of inequalities and say then that if I multiply this entire inequality by a positive number, we're good. And so then we're going to get -x squared is less than or equal to x squared times the sine of 1 over x is less than or equal to positive x squared. Okay? And so what have I found right now? Well, I've found that magical h of x that's always smallest, that magical g of x that's always largest, and our f of x that is trapped in the middle. Again, you could come over here and take a look at this. I'm going to delete these 2 guys out now, and I'm going to graph x raised to the second, x squared times sine x. I'm also going to graph y equals x squared. There's the bigger one. And I'm going to graph y equals -x squared. There's the smaller one. And if I zoom in on this, you can see that it actually does bound it. You have to get the axes right to really see it to make it pretty. But you can see that the blue parabola is the lower bound. That's our h of x. The red parabola, that's our, is it g of x? And then the green wiggly one, that's our weird x squared sine 1 over x function. But it's trapped in between. And as these 2 functions squeeze together, it's trapped there in the middle. And no matter how much I zoom in, do you see how it's trapped there in the middle? And it's trapped, and it's trapped, and it's trapped. You actually get a pretty cool looking graph. It has a weird looking 3-dimensionality to it. But what does that mean over here? Well, according to the Squeeze theorem, I can take the limit of this left-hand side, and I can take the limit of the right-hand side, and that should give me the limit of the middle. So what is the limit of negative x squared as x approaches 0? Well, that's just direct substitution, 0. And so then what is the limit of positive x squared as x approaches 0? That is also direct substitution, 0. So that means that the limit of x squared sine 1 over x as x approaches 0 is somewhere between 0 and 0, or that limit must be 0, trapped in the middle. Right? All right, the last little thing. There are 3 special limits that we use in Calc 1, but are beyond Calc 1 to show that they're true, to prove that they're true, but we just run into them once in a while. And so these are just 3 special limits. There's nothing more that I can say about them than these are ones you just have to know. Okay? Sine of x over x as x approaches 0 is 1. 1 minus cosine x over x as x approaches 0 is 0. And this one, not as important as the other 2, but we do run into it. 1 plus x raised to the 1 over x as x approaches 0 is e. It's actually one of the definitions of how that number e has been found. All right, that brings us to the end. The end of, where are we? 2.3. Next video will be 2.4. See you back here for that one.